So where did the flood actually start? Now, for many of you, you might know that the International Conference on Creationism, that's the biggest creation conference in the world. It's held only once every 5 years. It was held in Cedarville, Ohio this year, and I was honored to be put on a panel talking about flood boundaries. So if you're at all interested in that presentation, this is the only place that it was recorded, is right here. Then knock yourself out. You can go ahead and watch it right now. However, the audio is a little bit ordinary. Thank you.
Well, I'd have to say, boy, am I in trouble. Because I got both sides that are going to be against me, as you'll see in this presentation. Okay, so this presentation is going to be a little bit different. You've been hearing about flood, post-flood boundaries, and you're going to continue to hear a little bit about that as well. I'm going to talk about the pre-flood flood boundary, and I'm going to do that using stromatolites to rethink the origin of the Great Unconformity. So essentially, the Great Unconformity, it doesn't really need an introduction. For most of you, you're probably aware of what the Great Unconformity is. Who knows what the Great Unconformity is? Hands up. Okay, so just about everybody. But if you don't, the Great Unconformity is basically a global surface of erosion. It covers most of the continents on the planet. And most creationists believe that it is the result of the onset of Noah's flood, as the floodwaters sort of covered the land. They also believe that the Great Unconformity is perhaps the best, or one of the best pieces of evidence for the flood of Noah. And that comes from my students as well. So this is from one of my students in a geology class that I was teaching recently. And in a discussion board, he said this: we would then find in the layers above the Great Unconformity a sequence of Cambrian rocks, sandstone, shale, and limestone. A sequence like this is known as a transgressive sequence, and it represents the transgression of the ocean onto the continents. And this would be proof of Noah's flood. And this is pretty standard. It's pretty standard with my students, and it's pretty standard with most creationists that I meet. It's the Great Unconformity is kind of like a no-brainer. So you're probably scratching your head, thinking, well, if the Great Unconformity is a result of Noah's flood, then what is this guy wasting our time for? Why are we talking about this? And it's because of these things. As Andrew Snelling once said, the pesky little stromatolites. So this is what I did my PhD dissertation on. These ancient stromatolites are typically, but not always, sort of columnar or domed sort of structures that look like this. You can see them on the board there. They're made of carbonate mud, which is like a fine limestone, and they grew in near-shore environments through the action of photosynthetic microbes. And if you want to talk to me about that later, then feel free to do that. And I do have, I was going to bring it with me, but I actually have a piece of one of these stromatolites. It's about that big, and it's by my poster over in the poster hall. And you can go there and pick it up and touch it and feel it and have a look at the fabrics in it for yourself. Now, the problem is that there are thousands and thousands of these ancient stromatolites in growth position just above the Great Unconformity in sediments that were apparently deposited in the flood. So here is an example of a geologic column. So this geologic column is one that I drew up from my research site in Utah. And, do I have can I get the... Yeah, thank you. Okay, so here is the geologic column. This is actually the Notch Peak Formation. It is about 1,500 feet thick, and the top 450 feet are filled with many, many layers of stromatolites. So actually, this is what I did my research on, just this 154 meters. So that is, that's actually 450 feet. That's 1,000 feet. So that 450 feet has 12 distinct stromatolite layers in it. So this is a blow-up here of this. And you can see you've got a stromatolite layer there, which is about 15 feet thick. Then you've got a waxstone layer, which is sort of non-fossiliferous. And then you've got another stromatolite bed, and then you've got a waxstone bed, and another stromatolite bed, and so on and so forth. So you have 11 distinct layers just here in this 450 feet, and there are a bunch more layers above it. So maybe, upwards of 20 or 30 different stromatolite layers, and each one of these layers are at least 3 feet up to maybe 15 or 20 feet thick of stromatolitic material. This is actually my research site here. It's in western Utah. That's where I did my research. And this research so far has generated 4 papers. So there is a paper in Palaios, a paper in Faces, so they're secular journals. And it's also generated 2 papers in Christian creationist literature. So 2018 ICC, there was a paper there. And also most recently, 2021 Answers Research Journal. And that would be the one that I would go to because it's most recent. But if you want to look at those papers, go to my website, creationunfolding.com, go to my publications, and you'll see my publications there, and you'll be able to click on the ICC paper and the ARJ paper and download them on your phone right now if you wanted to do that. However, if you do the ARJ one, I can tell you it's going to take you a little while because it's about 16,000 words long. But it's pretty informative, so go ahead and do that. The other 2, I'm afraid, you're going to have to pay for. So let's take a look at these stromatolites. So the next few slides are going to come from this bed right here, bed number 11. So I did my research primarily on this bed and on this bed right here. So we're going to look at this bed right here at the top. So what you're looking at here is like a grove of these stromatolites. And so here's a stromatolite, here's a stromatolite, here's one here. And this grove is exceptionally well preserved. The way the bed has weathered out, it actually looks like what they would have looked like in growth position. You can actually see them in 3-dimensional form, which is really, really cool. So you've got the stromatolite here, and you've got the interspace material, which is this stuff. And then you've got the substrate right below them, which is what they grew on. So this is a nice little patch in that bed. And they're really extensive. So this is actually a drone picture right here. That's about 3 feet or a meter. So this is about 40 feet by about 30 feet to give you an idea. This is a close-up shot of this surface. And you can see these sort of round, oblong-looking circles. They're stromatolites. And they're all closely packed together with these kind of thin interspaces, which are typically filled with trilobite hash and shells and brachiopod, bits and pieces and excuvate and sort of things like that. And these are the stromatolites. Now in this section of the bed, you can see it's nice and flat. And that's because that section of the bed has been eroded flat. And it allows us to sort of see inside the stromatolites. In this photo, that's not the case. You can actually see the entire stromatolite, including the domed top. So what I want you to see, though, is you can see these little circles. Okay? You can see them pretty clearly there. But what I want you to see is they actually cover that entire bed. There are hundreds of them just in that photo, and I actually correlated this bed over a wide area, about 20 square kilometers, so about 8 square miles. So there were hundreds, thousands of these stromatolites just in that small region. But my colleagues, Art Chadwick and Leonard Brand, you guys are probably familiar with them, they were able to correlate this bed, or a bed that was closely associated with them, over an area of about 2,600 square kilometers or 1,000 square miles, and that's what that red box represents. So now you've got 1,000 square miles of tens of thousands of stromatolites in multiple beds that creationists have looked at. But it turns out that secular scientists have done a bunch of research on this as well, and the black box up there represents a correlated stromatolite assemblage here that covers the entire area in that black box. So going from eastern California through Nevada on into western Utah. So we're talking about hundreds of thousands of square kilometers of stromatolites that are multiple layers, multiple horizons with hundreds of meters of thickness of stromatolitic material. But we also see them all over North America. So the red dots and stars represent stromatolitic locations, and these stromatolites can be hundreds of square kilometers in a real size, and multiple different layers, just like they are over in Utah. And you can see these stromatolites, they sort of go in kind of a nice arc around this black line here. And this black line actually represents the outline of Laurentia, the ancient continent of Laurentia. So it's interesting that they sort of follow the coastline, which is why secular scientists and I too interpret them in terms of shallow marine in situ growth. So we've got 31 distinct sites. They start off in Newfoundland, they proceed down south to New York, Maryland, they travel from Tennessee to Texas, and then to the regions around Utah, California, Nevada, and of course they continue then up through Idaho, it looks like, Northwest Territories, right the way through there. So lots and lots of these stromatolite locations. And by the way, the blue color, that represents the Tapeats sandstone equivalents. So the Tapeats sandstone is the sandstone that appears right above the Great Unconformity, and this is all the sandstones that sort of join onto it. They have different names, but it's their equivalents. And you can notice that most of those locations are sitting right above the Great Unconformity. And they're also all over the world. So these stromatolites, this is a picture of North America, but you can find them just about every continent, I think, except Africa, all over the world. So there are lots and lots of these Upper Cambrian stromatolites. So here's what I really want here to dispel a creationist myth. And the creationist myth goes something like this. There are huge assemblages of stromatolites in the Precambrian, but there are none in the Cambrian, or none in the Paleozoic. The second myth goes something like it, and it's that there are huge assemblages in the Precambrian, but there are just a few in the Cambrian or the Paleozoic. I hope I've convinced you, just with the pictures that I've showed you, that there are huge, massive assemblages of stromatolites in the Cambrian. They're actually in the Ordovician as well. And this is actually an article from a secular scientist. This is Shannon Peters. And he wrote a paper that creationists typically are familiar with on the Great Unconformity. I don't know if you're familiar with the Gaines and Peters paper from 2012, but he's one of those authors. And he said this about Paleozoic stromatolites. That's what the quote is there. Stromatolites continue to exhibit large changes in prevalence after the evolution of metazoans. So metazoans, that's from the Cambrian, right? That's where we see metazoans. And they transiently achieve Proterozoic-like prevalence during the Paleozoic. That's a secular guy. If you don't believe me, if you think that secular science is more authoritative. They're saying that Paleozoic, when he says transient, he means because we find them all in the Cambrian and the Ordovician. You hardly find any above that. But you find them all in the Cambrian, most in the Cambrian, but a whole bunch in the Ordovician as well, and then they just sort of stop. But they reach Proterozoic-like prevalence. So, can we please, creationist scientists, writers, let's dispel the myth that there are not many stromatolites in the Paleozoic. Hopefully we can do that. Okay, so that brings us to solutions. So as you can imagine, I've been wrestling with this as a creationist for 10 years. What do we do with all of these stromatolites? How do we interpret the processes that form the Great Unconformity, and where should we put the pre-flood flood boundary? Because you simply can't have all of those stromatolites growing in the very initial stages of a global flood. So the growth rate solution says, well, maybe they just grew really, really fast. Well, we do have stromatolites today. They're not the best analog to use, but it's the best we've got. And they grow fairly slowly. So they grow 0.5 to 36 centimeters, 0.5 centimeters to 36 centimeters a year. About 0.2 inches to about 14 inches a year. So let's call it a foot. Okay, maximum rate of growth is a foot a year. If we just take this portion from my research site that I did research on, and we just add up the stromatolitic material, not the waxstone beds, just the actual stromatolite, there's 150 feet thick of just growth material, stromatolitic material. Well, even if we multiply this by an order of magnitude, let's call it 1 foot, that would be 120 foot in a year. That's one order of magnitude. Okay? So you're getting close to all of that. By one order, sorry, not by one, that's 2 orders of magnitude, right? 1 order of magnitude is just 12 feet. So 100 times, and we still only get 120 feet in a year, and we haven't included any of this stuff. There's probably another 150 feet thick there, and we haven't included any of these, because this is the Notch Peak Formation. That's all of this. That there is in that box. This is 2.6 kilometers thick of carbonate material, limestones. And there are other stromatolites below and other stromatolites above. So I hope we can sort of see the problem we're going to have with any kind of growth rate solution. Unless you're going to think of supernatural growth, God can do anything he wants, but we're here trying to investigate this using science, then that alternative is not going to work. And that alternative gets worse because these stromatolites are actually found in Upper Cambrian deposits. So here is the geologic column, and here is the Upper Cambrian, this red box here. So you've got all these stromatolites in the Upper Cambrian. This is the current, model for the flood. Okay, starting from the Cambrian-ish up to the Cretaceous, and of course the higher flood model will take it right up to the top of the Neogene. They're all the flood rocks. So thinking about the flood in terms of multiple 100-foot high tsunamis that are sort of smashing into the continent of North America, carving up 1 kilometer of the continent during the very early phases of the flood, that would mean then that, as John has said, he's calculated 136,000 sort of tsunamis, multiple 100-foot high tsunamis that are sort of eroding flat the North American Creton. That's going on at the same time that these things are growing. So you can see why you can't have both things going on. If we have hundreds of thousands of tsunamis tearing up the North American Creton, then you can't get all of this stromatolite growth around the world occurring. It's just not going to happen. And that's because that only represents a small portion of the 1 year. Right? So we're only talking here, if that's all flood rocks, then that's just going to be a month, 6 weeks, something like that. So your growth rate problem gets really, really hard at that point. Then there's the insoluble rock. So there's actually a picture. So you see lots of these pictures online of the sort of mega tsunamis that are sort of cavitating and carving up continents. And that's kind of the picture you envision. But I want you to imagine that, and now go back and look at those stromatolites. Imagine them growing in the midst of that. Okay? Can you guys see the problem? Can you guys see that there's an issue with that? But there are bigger issues with that as well, and that's because all of these rocks, let me go back. Here we go. These are all carbonates here. There's 2.6 kilometers thick of carbonates right down there in the Cambrian, supposedly the beginning of the flood. Well, I've done insoluble residue experiments on these rocks as part of my PhD. That's where you take sort of the carbonate, you put it in acid, and you see what's left. And we don't get dinosaur flesh in these rocks, you didn't know. But we do get quartz and plagioclase and muds, things like that. And they're called insoluble residues. And you can figure out, this is a scientific method of figuring out how far away the rocks were away from the shore by figuring out how much of this terrigenous material, like sand, is in these carbonate rocks. 3%. There is 3% of sand and silt and mud in these carbonate rocks. And I've looked in the literature, and that's true for this entire 2.6 kilometers thick. How do you get hundreds of thousands of tsunamis tearing up the crust, and where's all the siliceous material? Remember, this is down here. This is right at the base of the flood. This is when all these tsunamis are ripping up the continent. So I hope you guys can see that the growth rate solution, because of all of these things, the growth rate solution just doesn't work. Okay, the next solution would be, well, are they brought in from somewhere else? That's called allochthonous. Have they been transported? And the answer is no. Why? One of the best pieces of data for that is you can actually see them attached to the surface. So here's a stromatolite. This is one. This one actually, we took two of them actually back from the lab. Literally out of that 3D section where there was a little grove, we picked them up, we put them on a little trolley and carried them down the mountain. These things weigh like 150 pounds a pop, which is why they didn't float, by the way, for anyone who has that idea, okay? So these things were then cut in half. We cut them in half to have a look at the internal texture. And you can see these concavities. This is absolutely true of these stromatolites. They have these concavities, which is caused by the cyanobacterial growth. This is how they grow. But this is really interesting because this is the substrate right here. This is called grainstone, which is a really coarse-grained carbonate material. And I actually cut through, we took the whole base, we took this substrate back, as well as the stromatolite, so we could see where it was growing on. And we found the place it was attached. That's cool. Not just there. Here's a stromatolite. Now, it's a bit hard to see, you guys out there, but there are concavities here. It's a small stromatolite. You can see that's 5 centimeters there. There's a little elevated here. This is grainstone again. That's that coarser grained material upon which the stromatolites grow. There's a little elevated area. You can see that, like a little triangle. The bacteria like to take hold of these elevated areas on the substrate and grow there. And that's exactly what happened. And so this one, you have a stromatolite that grows up like that. You've got another one here, and you've got this grainstone interspace material between. These two stromatolites actually join together up here. You can see this lamination goes right the way across. Those two stromatolites actually grow into each other as you get further up the section. Here's a one that's so clear. You see that? That's the substrate, which is made up of ooids, which is a carbonate material. Kind of think of ooids like sand grains, except they're not sand. And here's a stromatolite clearly growing on the surface, attached to the surface. And what's interesting, these ooids have sedimentary features very much like sandstones. We find not just cross-bedding in these, but we find herringbone cross-bedding. In other words, showing the direction of flow was in two directions, multiple times, backwards and forwards, backwards and forwards. It's not a flood that was going on there. That's a shallow marine tidal environment. You've got this one here. So you've got, again, stromatolite. You can't see the concavities in this picture. Okay? And again, it's growing on an elevated area. And I'm not going to go into the other two. There are plenty of examples where they're growing and attached to the surface. Another problem, again, for the allochthonous position they were carried in, first of all, they're all upright. 100% of the time. The concavities are always concave down, which shows they have not been transported. They grew in that position. But not only that, they have different shapes. So these are the round ones you guys have looked at. This is kind of like a hexagonal, not exactly hexagonal, but they've got more straighter lines. And I've drawn the shape with red pen here. The interspace between these is only a couple of centimeters, really narrow, but they're not touching. How do you get stromatolites that have exceptional patterns ripped up from one location and then interlock like a puzzle in another location? No. And the same here. You've got these elongate ones that are fat, and I've gone ahead and I've drawn around them. Again, notice the interspace. Very, very consistent. Not pushing up against each other, like randomly distributed. And again, how do you get this jigsaw puzzle? It's like they were in that shape over here, and then they were transported and moved back into the jigsaw shape puzzle? No. And you've got these other elongate ones here. These are 15 feet long, these are 10 feet high and 20 centimeters wide. How do they travel along the surface on a 20 centimeter wide base without falling over? Okay, so no, you cannot have these transported. There are other transport mechanisms like megaclasts, and you can talk to me later, I can show you why that doesn't work either. Okay, so what's the solution? Well, right now, the pre-flood flood boundaries right here, Proterozoic to Cambrian, something like that. I propose we move the boundary higher. Now, I'm calling this a post-Ordovician boundary, and I say that because I don't really know where that boundary will be. And that's because no one's done any work on it. You know why? Because we assume this is correct. And that's the end of it. And I've written several papers, written lots of articles, made videos on this, and you know what I hear from people? Nothing. The myth continues. And so it's my pleasure to be here today because I want us as creationists, I'm a creationist, but I want us to start thinking about this. Have we got it wrong? What kind of new research, what kind of new ideas can we come up with if we move the boundary and we don't lock it in place? What about the great nonconformity? How do we explain the global surface of erosion? And John wisely talked about the fact you have these huge boulders, okay, on the great nonconformity. Can anyone think of another geologic time in history where we might have that form? Please. Creation week, thank you. It says this, let the waters under the heavens be gathered together in one place, let the dry land appear, and it was so, and God called the dry land earth, and the waters that were gathered together he called seas, and God saw that it was good. There is much more sedimentary deposits in Precambrian, lower Precambrian deposits than there is anywhere else in the geological column. That's a ton of geologic work. That's more than the flood. Why wouldn't the great nonconformity be put there? Okay, so for more information, you can go to my website, as I said. You can download those papers. I have made a 3-part video series. You can go there and watch that. Go to YouTube. You can punch in creation unfolding, then go to playlists, and then how much the geologic record was deposited during Noah's flood. That's my references. I'll go back to that slide just for a second if anyone wants to take a photo of that, and I'm done. Thank you.